Egunon, damos comienzo a la sesión plenaria de esta 14ª edición de las jornadas CPAN. Voy a ser muy breve, presento primero la mesa. Tengo a mi derecha a Fernando Plazaola, decano de la Facultad de Ciencia y Tecnología, donde estamos ahora. Gorka Moreno, vicerrector de Campus de Vizcaya. Y Toni Pic, que le conocéis bien. Bueno, simplemente primero daros la bienvenida a Bilbao, alrededores, ¿vale? Sabéis que Bilbao no tiene límites, entonces, bueno. Ahora mismo en Leioa. Es un placer teneros por aquí, tener a 200 mentes pensantes en la facultad, poner las patas arriba. De hecho, es interesante que los estudiantes pues, vean que la ciencia se mueve, que está hecha por personas como ellos, que es ciencia de calidad, en este caso en las áreas del CPAN, ¿no? Lo que nos ocupa. Y es un placer para el Departamento de Física, en concreto la parte teórica, que es más involucrada con el CPAN. Somos unos poquitos, pero activos. Entonces, bueno, es un placer tenerlos por aquí. Menciono a Gunnar Snell, que es compañero del departamento, que mano a mano hemos organizado estas jornadas, también otros colaboradores y estudiantes que se encargan de detalles que son importantes y bueno, eso, es un placer tenerlos por aquí. Y poco más. Bueno, quiero agradecer el apoyo de la facultad y de la universidad, ¿no? para tener estas jornadas, ¿no? Es una suerte. Y le paso la palabra a Toni.
Muchas gracias. Good morning, buenos días a todos. Gracias por venir, participar y traer todas las ideas que siempre lleváis cuando vais de un sitio al otro. ¿Vale? Hay física muy interesante que vamos a estar discutiendo en estas jornadas, pero ante todo quisiera agradecer al decano de la facultad y al vicerrector de campus por habernos facilitado estas instalaciones tan magníficas. Estamos realmente cómodos en este sitio. O sea, yo me he quedado impresionado de ver el campus, cómo está funcionando, el espacio. Está francamente bien. Quisiera agradecer también a los organizadores locales todo el esfuerzo que han hecho por traernos a todos nosotros aquí, y especialmente a Miquel García Echevarría y a Gunnar Snell. ¿Vale? Cuando me propusieron que viniéramos hacia aquí, pues no tenía muy claro cómo lo íbamos a hacer, pero han solucionado todos los problemas y está funcionando de forma muy eficiente. Bien, no voy a extenderme mucho, pero sí me gustaría aprovechar para recordar alguna cosa. ¿Vale? El CPAN, como todos sabréis, está funcionando en base a un acuerdo firmado por 27 instituciones, entre ellas la Universidad del País Vasco que nos acoja. ¿Vale? Por tanto, tenemos ese acuerdo, tenemos una serie de normas que todos los representantes legales han aceptado, y entre esas normas está el que toca ya cambiar la dirección del CPAN. ¿Vale? Son muchos años, pero hay que buscar un reemplazo. Entonces ya llevo 2 o 3 años avisando que hay que hacerlo. No me habéis hecho mucho caso. ¿Vale? Pero ahora sí, en enero pienso convocar una reunión del Comité de Estrategia. ¿Vale? Por tanto, aprovechar estas jornadas para discutir entre vosotros, y el objetivo sería en enero ya poder elegir un nuevo director o directora, ¿vale? Y de paso renovar la parte que toca del comité ejecutivo. ¿Vale? Entonces, tenerlo en mente, creo que es un buen momento para hacer el cambio. Tenemos muchos retos por delante. El EHC está ya funcionando en su tercera fase. Alta luminosidad no está tan lejos. ¿Vale? CTA está empezando ya los primeros datos, aunque con pocos telescopios. Hay muchas cosas y realmente hay que enfrentarlo. ¿Vale? Y FER, aunque está un poco más lejos, pero los retos están ahí. Bien, la otra cosa que sí me gustaría recordar, no todos son buenas noticias. Desgraciadamente, 2 de nuestros compañeros nos han abandonado prematuramente hace muy poco. Entonces sí que me gustaría recordarlos a los 2, tanto a Esteban Fulana, que nos dejó en julio, como a Vicent, que nos dejó justo la semana pasada. ¿Vale? Los 2 eran gente relativamente joven, sobre todo Esteban. ¿Vale? Espero que no no sigamos más por ese camino. Bien, dicho eso, el programa ya lo conocéis todos. Creo que hay cosas muy interesantes, por lo tanto vamos a ver lo que hacemos y cuáles son las novedades más importantes. Y con eso acabo y le paso la palabra a Fernando.
Eskerrik asko, Antonio. Bueno, Bizkaiko kampuseko errektore ordea, Gorka Moreno, CPANeko koordinatzaile eta Valentzia Unibertsitateko katedraduna Antonio Pik Zardoia, eta nire ezkerrean, danok ezagutzen duzuten, Mikel Etxeberria. Egunon guztioi eta ongi etorriak izan zaitezte UPVEHUko Zientzia eta Teknologia Fakultatean dagoeneko atzo ezkero martxan dagoen jardunaldietara. Izan ere, 14 jornadas del Centro Nacional de Física de Partículas, Astrofísica y Nuclear, izen luzea, CPAN, jardunaldietara. Uno de los objetivos de estas jornadas, que os reúne a vosotros, es decir, la comunidad española integrada en la agrupación CPAN, es potenciar la cooperación de grupos españoles de investigación y articular de forma conjunta las líneas prioritarias de actuación de las diferentes redes, que por lo que he visto en el programa son la de física del LHC, física de astropartículas, y física nuclear y física teórica, es decir, 4 redes. En relación al Gran Colisionador de Partículas, que recientemente, como bien sabéis, en julio pasado comenzó un nuevo periodo de funcionamiento, se presentarán en estas jornadas los resultados obtenidos en este nuevo run. Y si no recuerdo mal, en el experimento Atlas de este acelerador en su primer run, se detectó por primera vez hace 10 años el bosón de Higgs, por lo que en estas jornadas conmemoráis el 10º aniversario de ese hito. Como bien sabéis, además, esta partícula fue predicha independientemente en 1964 por 3 grupos de investigadores en los que se conoce como los artículos de 1964 de PRL sobre rotura de simetría. La partícula y el mecanismo llevan únicamente el nombre de uno de los investigadores, pero conviene recordar, como ocurre muchas veces en la ciencia, que los investigadores que dieron lugar a que este hito se produjera, o esta predicción se produjeran, fueron Keeble, Gulalnik, Hagen, Engler, Broad y el propio Higgs. Este descubrimiento sirvió, como bien sabéis, para fortalecer y cerrar el modelo estándar de partículas elementales. Pero en estas jornadas también discutiréis sobre temas que se escapan del modelo estándar, como por ejemplo la materia oscura, presentando los resultados obtenidos en los experimentos que se llevan a cabo en el laboratorio subterráneo de Canfranc para la detección de la misma. La física del neutrino tendrá también un espacio importante en estas jornadas. Hace 3 o 4 semanas investimos a Jocelyn Bell Barnell, doctora honoris causa de la Universidad del País Vasco, Euskal Herriko Unibertsitatea, es decir, de esta universidad, a propuesta de esta facultad en particular, a propuesta de lo que entonces era el Departamento de Física Teórica y todavía seguía más, e Historia de la Ciencia, y le hicimos una pregunta. Y la pregunta que le hicimos es, en su opinión, ¿cuál es el mayor reto de la ciencia en estos momentos? Y ella respondió sin dejar resquicio a la duda: la física del neutrino. ¿Y qué vais a tratar aquí? Adicionalmente, habéis introducido en el programa una sesión de transferencia de tecnología que acaba de terminar esta misma mañana, en la que mostráis a la sociedad que la financiación pública de la ciencia básica es fundamental. Y lo vuelvo a decir, la financiación pública de la ciencia básica es fundamental. Cierto, como digo, y de hecho puede dar frutos muy importantes en temas directamente relacionados con el bienestar humano, como lo habéis demostrado en las sesiones que acaban de terminar esta mañana. Es decir, esta mañana habéis tratado, por ejemplo, sobre la diagnosis y terapia de enfermedades como el cáncer, que parecen muy lejanas a lo que estáis tratando en las otras sesiones paralelas. Y gracias a los nuevos conocimientos obtenidos en los problemas de ciencia básica que se tratan en estas jornadas, se ha facilitado, por ejemplo, un grandísimo avance en medicina nuclear. Asimismo, la divulgación científica tiene un papel importante en estas jornadas. Es un deber de los y las científicos difundir a la sociedad los nuevos conocimientos científicos que se están produciendo. Y en estas jornadas lo estáis haciendo con amplitud. En esta Facultad de Ciencia y Tecnología se imparten 10 grados y 14 másteres. Entre ellos está uno, el grado de física. Como bien sabéis, pues tiene asignaturas como la típica de física nuclear y de partículas y otras afines que están relacionadas con los temas que tratáis aquí y que es una buena cantera para esta comunidad de física nuclear. Y asimismo también tenemos el máster en ciencia y tecnología cuánticas que está también muy relacionado. Y mirando someramente la lista de participantes me he dado cuenta que de los 180 que me acaban de decir que habéis llegado a los 200, es un hito, 10 pertenecen a la facultad. Por lo que agradezco al comité organizador y entre ellos particularmente a Miguel y a Gunnar por todo el esfuerzo realizado para que estas jornadas sean una realidad en nuestra universidad y particularmente en esta facultad, así como a los investigadores e investigadores invitados y a todos y a todas las participantes. En particular doy una especial bienvenida a todos y todas vosotros que venís de fuera del País Vasco. Y espero que estos días os sirvan también para conocer un poquito mejor el País Vasco, a su gente y a su cultura y, cómo no, que disfrutéis de su gastronomía. Eta amaitzeko egingo dut euskeraz, herriko hizkuntza entzun dezazuen naiz ulertu ez, aipatu berriro ere oso garrantzitsua dela guretzako zuek ona etorri izana. CPANen 14. jardunaldiei etekin handia atera iezaiozue. Disfrutatu egonaldia eta urrengo batera arte. Eskerrik asko guztioi.
Bueno, Fernando Plazaola, Zientzia eta Teknologia Fakultateko dekanoa, Antonio Pik, director de CPAN, Miguel Etxebarria, talde antolatzailearen izenean. Lehenik eta behin egunon guztioi eskerrak eman nahiko nizkioke bai fakultateari eta bai fisika sailari egindako lanagatik eta maila honetako kongresu bat bertan egiteagatik. Mil esker, gonbidapenagatik, mil gracias por la invitación para poder participar en este acto de inauguración de esta 14ª edición del Congreso de CPAN. Para mí es un placer y es un placer también, y antes lo comentábamos antes de iniciar el evento, que se puede hacer aquí en Leioa, porque al final es verdad que la Universidad del País Vasco y el campus de Vizcaya tienen en Bilbao una sede como puede ser el Vizcaya Aretoa, y yo diría que se han convertido en el centro y en el imán para la organización de congresos, para bien y para mal, diría yo, y muchas veces se nos olvida que tenemos un campus, como subrayaba Antonio, bonito, grande, y en el que hay espacios como estos tan atractivos para poder organizar eventos de este tipo, ¿no? Entonces, que demostrar, como decía también Javier, que el campus está vivo. Él hablaba de revolucionar la facultad, que se pueda revolucionar también el espacio de Leioa, creo que es importante. Antes de proseguir voy a hacer una confesión que no parte de la falsa modestia, y es que soy la persona que menos sabe de estos temas de física de partículas, astropartículas. Vengo del ámbito de la sociología, así que os podéis imaginar cuando he leído acelerador de partículas, bosón de Higgs, pues bueno, cuando el acelerador de partículas, pues sí que en algún momento en los medios de comunicación ha estado el debate o la controversia por la ubicación geográfica. Pero más allá de eso, y esto tiene también una mala noticia añadida para vosotros y vosotras, y es que no me voy a poder presentar a la candidatura para ser nuevo director del CPAN, así que tendrá que salir de este espacio, tendrá que salir. Dicho lo cual, y como os podéis imaginar, no voy a entrar en contenidos específicos como ha podido entrar Fernando, que sabe de este tema. Sí que me gustaría subrayar dos aspectos. Uno de ellos, que también Fernando ya lo ha subrayado, y es la importancia que le dais en el Congreso a la transferencia. Muchas veces se hace, iba a decir, una división ficticia, quizá no ficticia, pero yo creo que poco fructífera entre lo que son la ciencia básica o la investigación básica y la ciencia más aplicada, que creo que hay que romper, ¿no? Y en el caso de este ámbito en el que se puede pensar sobre todo en ciencias básicas o en investigación más básica, creo que es importante subrayar también que en los TRLs más avanzados, en la transferencia, tenéis mucho que decir, ¿no? En ese sentido, yo siempre traigo a colación las palabras de un exrector que hablaba que él no diferenciaba entre investigación básica o aplicada, sino entre buena y mala investigación, y creo que buscar sinergias entre lo básico, lo aplicado y esos TRLs más iniciales y últimos, creo que es importante. Y en segundo lugar también me gustaría subrayar que en el Congreso haya lugar también para los estudiantes y para sesiones más divulgativas, ¿no? Más allá de que estudiantes predoctorales puedan presentar sus ponencias y comunicaciones, que pueda haber sesiones más divulgativas, creo que es importante que tengan impacto sobre el alumnado, el estudiantado de la facultad. Creo que son elementos que tenemos que subrayar y que son importantes. Como ya se ha dicho, 200 personas, no es fácil organizar un evento de este tipo, el poder juntar a una comunidad de personas expertas en este ámbito, y también, como apuntaba Fernando, espero que podáis aprovechar y conocer mejor Bilbao. Si tenéis la suerte de quedaros el fin de semana, bueno, pues poder incluso conocer los alrededores, ¿no? Tenéis lugares muy, muy bellos y bonitos, y la verdad es que creo que vale la pena. Y por ir acabando y no extenderme más, estoy seguro que los debates y las ponencias, tanto parciales o en subgrupos como plenarias, van a ser de gran interés. Para nosotros y para nosotras, tener un evento de este tipo y de estas características aquí es muy, muy importante. Y como suelo yo subrayar en muchas ocasiones, creo que este es un claro ejemplo de cuál es el lema de nuestra universidad, que cada vez, por cierto, me gusta más: emanta zabalzazu, edad y extender. Creo que en dos palabras se recoge muy bien esa idea del vínculo que tiene que darse entre lo que es la formación, la investigación y la transferencia. Sin más, besterik gabe, CPANeko 14. Kongresu hau inauguratutzat jotzen dut, doy por inaugurado esta 14 edición del Congreso CPAN. Mila esker, eskerrik asko guztioi, gracias. Muchas gracias por invitarme.
¿Dónde está el botoncito? ¿Dónde está el botoncito? ¿No se encienda? ¿Dónde?
Esto se mute por si un momento quieres.
Thank you very much to Antonio and Fernando. So let's start with the scientific session of the plenary session. So we will start first with the talk by Abelardo Moralejo from IFAE, who will present the first observation with the LST-1, the prototype large-size telescope of CTA. So let's see how we manage this.
Me gusta más esto, que sea así.
Este de aquí.
Aquí mismo, aquí. Hello, can you hear me?
Te aviso cuando te queden 10 minutos.
Sí, okay. Okay, thank you very much, Isabel. First, I want to thank the organizers for this opportunity to present the status
and the first observations with LST-1, the first large-size telescope of CTA. I'm doing this presentation on behalf of the CTA-LST collaboration. So first, a reminder of what is CTA. CTA is the Cherenkov Telescope Array, and it's the next generation installation for gamma ray astronomy in the very high energy range, which means basically photons with energies larger than 20 GeV. And the concept of the instrument is simply a large array of atmospheric Cherenkov telescopes deployed over an area of the order of 1 square kilometer. And these are atmospheric Cherenkov telescopes of different sizes in order to cover a large energy range. Yeah? So specifically LSTs, the largest, will cover the lowest energies. The detection principle, you probably know, it's simply to detect the Cherenkov light produced by the particles in the showers initiated in the atmosphere by gamma rays. So there are a few of these instruments around the world, but when completed, CTA will have a factor between 5 and 10 higher sensitivity than all existing facilities. Okay, CTA aims at having full sky coverage, and therefore we need an observatory in the northern side, in the northern hemisphere, and in the southern hemisphere. The one in the southern hemisphere is close to Cerro Armazones in the Atacama Desert, in this area here. And the one in the north, which is most interesting for us, is in the Roque de los Muchachos Observatory. This is an artist's impression of how it may look like in a few years. And it will consist in the so-called alpha configuration, the first implementation of 4 large-size telescopes and 9 mid-size telescopes. The Spanish groups are mostly involved in the construction of large-size telescopes, but also in some parts of the MSTs as well. The LST collaboration, it's a collaboration within the CTA consortium. It's formed by around 300 scientists from all these countries here. And we have the commitment to build 4 LSTs in CTA North. The funding is ready for that, and actually the instruments are nearly built, will be deployed in the coming years. And also some LSTs in CTA South. So far there is funding for 2 such instruments, but the final goal is to have 4 as well in the south, same as in the north. Good, so what's the status of the project? CTA at large will be constituted as a CTA-O, the O stands for Observatory, ERIC in late spring next year. But nevertheless, the construction started ahead of this ERIC constitution. So as early as 2018, we inaugurated the first LST, which you can see here in this recent picture, in the Observatorio del Roque de los Muchachos. And I have to clarify that in the title I say the prototype LST, but this is a fully functional and fully equipped instrument. So it's actually the first telescope of CTA in a CTA site. Okay? So we have been in commissioning since this date here, so it's pretty long commissioning, but it was impacted by different things, the pandemic, of course, the inflation, component crisis, and also the volcano eruption in case something was missing. Nevertheless, we managed to take like 800 hours of sky observations during, since this period here, when the telescope became fully operational. And we have not yet reached the target data taking efficiency of 95%. We are more in 70% or so. And this is mainly due to still not completely stable and functional control software. The all 3 telescopes, LST-2 to 4, are under production. Many parts are ready. I will come back to this in the end. And I'm happy to announce that the civil works, after some delays due to the permits and things like that, started 2 weeks ago in La Palma. For LST South, as I mentioned, we have funds secured, mainly of Italian origin, for 2 LSTs. So we are quite confident that we will have also LSTs in the CTA South side. Okay, this is just a reminder of what happened in La Palma in September 2021. This area here, formerly known as Cumbre Vieja, erupted somehow. This lasted for about 3 months, and this completely stopped our commissioning. We had to protect some delicate parts of the instrument to avoid the intrusion of ashes or things like that. And we were actually, let's say, grounded for more than this time. We resumed operations by the end of January 2022. Fortunately, the eruption was rather far, like 15 kilometers from the observatory, and also quite lower, like 1 kilometer lower. So it did not produce any permanent damage, and we are back in operation. Okay, so what is it that we see with CTA? Okay, this is not the right slide. Maybe I can change it because this is the PDF and not the PowerPoint. Just a second. It should be here. Okay. Okay, this is a bit nicer. What LST1 sees when it looks up, it's actually this thing, okay? So we're recording the Cherenkov light from particles in showers initiated in the atmosphere by gamma rays, but more than gamma rays, what we see when we start taking data is mainly showers initiated by protons and other charged cosmic ray nuclei, which are not very useful for astronomy. They are our background. And so this is what you're seeing here. This is just 6 selected events from 1 minute of data taken of 2 years ago. And yeah, what you can see here are essentially hadronic showers. Here you can see one with 2 electromagnetic subshowers. Here you can see some atmospheric muons, so these muon rings with a parent shower also here. And also particularly interesting are isolated atmospheric muons that produce a single ring. And that for most of you are a nuisance in your work, for us in part are a blessing, because this allow us to do some cross-check or some calibration of the telescope. It's rather easy to forecast what the light yield of a single muon on the telescope is, if you know the geometry, mainly the radius, and then you can, let's say, calibrate the telescope with that. We cannot put our instrument in a test beam because the atmosphere is part of it, but we have at least these muons that allow us to calibrate the light collection efficiency of the telescope and also the last part of the atmosphere, the transparency of the last part of the atmosphere. So we do this regularly. This is a plot in which each point is data run, and what is shown here is the optical efficiency of the instrument as estimated from the muon rings. And this is simply run numbers, so this is not really time, so that's why you don't see gaps. And what we can see is that these variations of the efficiency are within plus minus 5%. There are some sudden changes here. First, we were worried after we resumed operations following the eruption that this could be a permanent damage of a few percent. But then a few weeks later, we had some rain and things recovered. So it seems that the telescope has not suffered any major damage, and actually its performance is rather stable within plus minus 5% in terms of light efficiency in the data we have taken so far. Okay, so these variations are, well, of course, this is a telescope without a dome. It's in the open air. So the variations may be due to things like dust deposition from Kalima, or occasionally misfocused mirror tiles. So there are many things that affect this. Yeah. Okay, so what else? As I said, what I showed before in the previous movies were mostly background cosmic rays. We are interested in the gamma rays, which are a very small fraction of what we see, of the order of 1 every 10,000 events or so. And how do we select the gamma rays? Well, our baseline analysis is based on the so-called Hills parameters. They are simply the moments up to third order of the light distribution on the camera after some image cleaning. Okay, so these basic parameters and also some parameters based on the times of arrival of the signal on pixels are passed to some classification and parameter regression algorithms, specifically those called random forests, that we train on Monte Carlo simulations, okay, that have been tuned to the performance of the instrument, mainly using muon rings. With this, we can obtain reconstructed parameters for each event, so the direction of the shower, which should match the direction of the primary, the energy, and also the nature of the primary with a parameter we call gamma-ness, which is simply a score between 0 and 1, which is, it's close to 1 for gamma rays, which is what we are after. Okay, so this is basic sketch of how we do the analysis. And then with this tuned Monte Carlo simulation, we can check what is the performance of the instrument versus true energy. So in these plots here, the x-axis is always true energy. What we see here on the y-axis is the angular resolution. You can see it's pretty dependent on the strength of gamma ray selection cuts. Here, The blue angular resolution is for relatively strict gamma ray selection. And you reach resolutions for the middle energy range, which are close to 0.1 degree. This is the effective area. You see it's of the order of tens of thousands or hundreds of thousands of square meters, so much larger than any spaceborne instrument, for example. And this is the energy resolution, okay, which in the, let's say in this range here is around 20%. All these parameters, if you check, they are not better than those of currently operating Cherenkov telescopes, and this is because we have a single telescope. A stereoscopic reconstruction provides really a big advantage in this business, and therefore with, let's say, this performance is kind of competitive, but it's not better than existing instruments. The only exception may be physics cases in which you need very low energy threshold, which is an advantage of the large dish of LST1. And one example is GRBs, of course. Note that here down to 20 GB, we have effective areas which are well above 1,000 square meters as compared to typical 1 square meter for space instruments. Okay, the other important parameter is the flux sensitivity. We can test this directly with real observations. I said we don't have a test beam, but we do have a standard candle, which is the Crab Nebula. Crab Nebula is this remnant of a supernova from 1054, and it's a powerful, very bright gamma ray emitter in very high energy range. And it's also, so far, stable. So we use it as a standard candle. You can observe it with LST1. We did it, and from observation of 34 hours over 1.5 years, we can determine what is the minimum flux in terms of percent of this flux of the standard candle that we can observe in 50 hours, okay? A statistically significant signal in 50 hours. And okay, this is what we get with some definition of this sensitivity, which is basically 5 standard deviations in 50 hours and 2 different analyses. And as you can see, when you compare to MAGIC, we are still worse. I mean, the minimum flux we can see is higher than that MAGIC can see. And again, this is due to this lack of stereoscopy. This is going to change radically when we build the second LST, the third, and the fourth, yeah? And then the additional MSTs. Okay, nevertheless, we can do some physics with it. So with these same observations of the Crab Nebula, we try to obtain its spectrum. So it's a spectral energy distribution versus energy. And the result from these LST1 observations are the black points here and the blue fit and the blue bands, okay? The dashed orange line is results from MAGIC in 2015. You see there is pretty good agreement, few percent discrepancy. And the magenta points here are from the Fermi-Lat Space Telescope. And again, there is pretty good matching, and you can see very well the complementarity between the two observational approaches from ground and from space. Okay. Good, so we think that LST1 then is more or less ready for science, as I said, competitive, but not outperforming current instruments. We are about to publish this LST1 performance paper based on the observations of the standard candle, and also working on a set of papers with observations performed during the commissioning period of several targets. Actually, one of them is already submitted to the journal. So what are these additional papers? Well, we plan to do one dedicated paper on the Crab pulsar. So besides the nebula, there is another gamma ray emitter at the center, which is the Crab pulsar. It's much weaker, but it's also interesting because it has this periodic behavior. This is a phaseogram that will appear also in the performance paper. But in the dedicated paper, we will do also spectrum and light curves and further studies. Again, this is a physics case in which low threshold of LST1 can provide us with an edge relative to existing instruments, because the spectrum of the pulsar is much steeper than that of the nebula, and therefore, okay, we can get closer to the range of space telescopes and make a more complete spectrum of the pulsar. So this is one of the papers. Another one is this pretty famous event, this NOVA RS Ophiuchi. Essentially, this is a system, a binary system formed by a red giant and a white dwarf, and the white dwarf is secreting material. And every now and then, in this case, every 15 or 20 years, there is a nuclear explosion, which produces gamma rays, as we will see. Okay, was actually a very nice event because it was first seen by an amateur astronomer with a naked eye, and he was the one who gave the alert. Immediately, many observatories around the world followed, among which LST1, and of course, our colleagues of MAGIC and HESS. So this is the spectral energy distribution, comparing the results from LST1 from those of MAGIC and HESS. Okay, so why is this thing emitting gamma rays? Well, basically the reason is that this explosion produces a shock, okay? And in this shock, via the so-called diffusive shock acceleration, charged particles, either protons or electrons and positrons, can get accelerated stochastically and then produce gamma rays, okay? Either via creation of neutral pions, which decay in gammas, or with inverse Compton, okay, of electrons and positrons on ambient photons. So this object is interesting because in a way it's a smaller and a time-compressed version of a supernova. So if we understand these objects well, our understanding of supernovae will also improve. And this is important because supernovae have long been believed to be the sources of cosmic rays in the galaxy. Okay, so one of the main physics goals of CTA is understanding whether it is true that supernovae in the galaxy are those replenishing the sea of cosmic rays in the galaxy. For this, there are two important things. One of them is to determine whether the emission, the gamma ray emission you may see in this case in this nova or in supernovae is of hadronic or leptonic origin, because in order to explain the bulk of cosmic rays, which are protons and other nuclei, you need let's say, to find evidence that the hadrons are being accelerated at these sources. Okay, so for this nova RS of Yuki, the very high energy observations of MAGIC and HESS and LST1, we are working on it. The observations seem to favor the hadronic models, which is very good news in order to advance in this issue of the origin of cosmic rays. Yeah? The other point that has to be addressed is whether the maximum energies of the accelerated particles in supernovae are high enough to explain the highest energies we see in galactic cosmic rays. And in the case of the nova, which is, as I said, is like a miniature version, again, the observations seem to show that the maximum energies predicted in models are actually reached. Okay, so the maximum energies observed are hundreds of GeV, and this implies that the parent particles have very likely energies of order of magnitude larger. Okay, so all this is very relevant for the understanding of the origin of cosmic rays. Good. Well, there were some recent news from past year in our field of very high energy and ultra high energy gamma ray astronomy, and it was this paper that appeared in Nature in May 2021 by the LASO collaboration, in which they reported the detection of 12 gamma ray sources significantly above, with energies above 100 TeV, which again implies that the parent particles are of energies like 1 PeV or so. Okay, so this is let's say, a good step forward in the understanding of the origin of cosmic rays, in the search for pevatrons. The point is LASO is an air shower array in Tibet, so it detects the particle component of the showers, and this is why it has to be very high. And it has very high sensitivity and also large instantaneous field of view, and it's working 24 hours a day. We can only operate at night. Okay, so it seems like all advantages, but of course CTA, even LST1 alone, has better angular and energy resolution and also lower energy threshold. So again, these are complementary instruments to what CTA will provide. CTA will certainly, by pointing at these individual objects, help understanding the emission mechanism. And we started doing this already with LST1. We took a long observation of 99 hours of one of these sources, this 2108 plus 51. This is point-like for LASO, so this is why it was chosen, because it was a better target for Cherenkov telescopes. And it's interesting also because there is no X-ray or very high energy counterpart so far. So LST was observing there for this long observation time. We didn't get any significant signal, just some hint at around TeV energies. But we have provided upper limits, which already constrain some of the early models. For example, this model was from the LASO collaboration itself, a hadronic model. And these upper limits from LST1 already kind of excluded. Of course, I mean, you have many parameters in this model, so immediately there is another hadronic model that can fit, okay? So it's still not clear whether this source is hadronic or leptonic, let's say, dominated. But, okay, we will keep observing with LST and with further telescopes. This is the paper I mentioned that is already submitted. So, okay, as I said, we are already starting to do science with CTA. So this was for galactic sources. We also observed things beyond our own galaxy, and this is an interesting event. It's actually the first and so far only astronomical telegram submitted by CTA, and it's a flare of an active galaxy called BL-LAC in 2021. This is just a so-called theta square plot where you can see the significance of the excess compared to the background. And okay, this is a source which, well, it's an active galactic nucleus of the BL-LAC type. It's actually the proto or the archetype of these objects. And of course, they are interesting as possible sources of ultra high energy cosmic rays, neutrinos, and so on. Okay, so we kept observing this source. In August the same year, it reached even higher fluxes. So this is the Standard Candle Crab Nebula, which is the brightest source by far, usually in the sky in gamma rays, and this object BL-LAC reached fluxes of 4 to 5 times and brighter than the crab for some days. Yeah? Okay, so this is also work in progress, and a paper dedicated to this source will also be is also on the line. Yeah? Okay, there are other transients which are very interesting. Most interesting, perhaps, GRBs, and also very adequate for observation with the LST1 because of its low threshold. We were pretty unlucky, actually, with this GRB 221009A, the so-called brightest of all times. It was an incredibly nearby and bright GRB that happened a couple of months ago, but it arrived during full moon. So that was very unlucky for us. There was not even a shift crew. We had to organize something urgently and could observe only the following night, which means 30 hours later, and in very challenging conditions because it's a very bright moon. We had to operate with lower high voltage on PMTs and everything. So this, okay, analysis is ongoing, but fine, we arrived pretty late. So I think it will not be really so exciting. Yeah? Of course, if what I have discussed so far was a bit too, let's say, astrophysical for your taste, keep in mind that things like detection of GRBs, especially if we catch the prompt phase, would have very interesting consequences, possibly for fundamental physics. For example, we could provide strongest tests of Lorentz invariance through tests of the possible dependence of a speed of light with energy. We are also following other transients like neutrino events, galactic transients, and fast radio bursts. Okay. Good. So this is what we are doing with LST1. Of course, we are looking forward for the 4LST subarray, which will really be by far the strongest instrument of its kind ever built, and then afterwards to the full CTA North array. So when is this coming? Well, as I said, most of the pieces for the remaining 3 LSTs are ready, are in warehouses or being integrated in different labs. You can see here, for example, the cameras, okay, that are well built mechanics at CMAT, then integrated at IFAE and sent to IAC. So they are nearly ready, all 4 of them, for installation. This is also the camera arc, different elements. So basically, the components are mostly ready, and as I said, the civil works have just started. This is a schedule of the installation, just to announce that we expect to have LST 2 fully operational by the end of 2024, so more or less here, and the other 2, LST3 and LST4, operational by the end of 2025 or early 2026. Okay, and this is what will be, for us, really a game changer, okay, in all physics cases. Good, so I'm coming to the end. These are the conclusions. So LST1, the first telescope of CTA North, is up and running with a performance that fulfills the expectations we had before constructions, and we're already working on the first papers with the performance paper very soon to be submitted. As I said, remaining LSTs in CTA North are coming in 2-3 years, okay, and this will provide a large boost of performance thanks to the stereoscopic reconstruction. And as I said, we expect also to go for the south with 2 LSTs which have got funding, and it's actually funding with, let's say, very short spending period, so at least the manufacturing of parts should finish also before the end of 2025. Okay, so that's all. Thank you.
Thank you very much for this nice talk. So I guess there will be some questions, please.
Hi, I wanted to ask you if you can clean the mirrors of the telescope, and if you can, how many times per year?
That's a good question. We've never done that, so we just pray for having rain, and if possible, clean rain, because in La Palma sometimes rain just brings down on you the desert dust. So we're not doing that, also because they are relatively delicate, okay? There is some research being done on mirrors which are more robust, a surface which is, let's say, that you can really clean, or with a jet or whatever of water. But this is work in progress. I mean, the current ones we don't plan to clean. We plan to replace mirrors every now and then, and this is already happening because this telescope has been in the open air for 4 years, okay?
Hi. I thought that first CTA, now CTA South was approved, and then CTA North was added sometime afterwards. Maybe I'm mistaken, but it's not true.
No.
Oh, okay.
No, the so-called alpha configuration, which is the one that was announced when the in-kind contribution of everything needed was, let's say, granted or was secured, was simultaneously for North and South. So, yeah.
But from your description, I understand that CTA South is not as far ahead as CTA North, or how is it going?
Correct, but I didn't mention it because we are more involved in the North, obviously, but the construction of roads, access roads, has started already. It's more complicated because the area where it will be built is a real desert. I mean, it looks like Mars, really. There is nothing. Whereas in the north, we already had telescopes there, so it's easier. But the road construction has started, so I don't have the detailed schedule there, but the idea is that from the moment the ERIC is constituted, so as I said, late spring 2023, in 5 years, more or less, you should have CTA South also deployed. Okay, so 2028 maybe?
Yes. Is the Bingo radio telescope in Brazil going to join the CTA?
I have no idea. I don't know. There is Brazilian collaborators in CTA and LSD, but I don't know if. I guess there will be collaboration because there are contacts with very different instruments, but I don't know any details. Sorry.
Can LST1 already send alerts to the community, or are you
working on that? But first, I think the first priority, as I mentioned briefly, is to automatize the following of alerts, actually. Because LST1 is a narrow field of view instrument, so it's not so easy that we are the first to see something. No? Typically, we follow alerts from satellites, okay? And our priority now is before the end of the year to make this automatic like it is in MAGIC. No? In MAGIC, we managed to get a GRB half a minute or 40 seconds after the start time, and this is the aim also for LST.
Okay.
By the way, I didn't mention it, but this burst, brightest burst of all time, it was a real pity because it even had a precursor like 1 minute before that would have triggered already this following. So we would have been pointing with magic, yeah? I mean, not with LST because we were not ready, really when the main activity started. So it was really tragic, yeah.
I have another question, if you don't mind. Yeah. When you saw the plots for the angular resolution...
Where is?
I'm here again.
Okay, yeah, sorry, again.
when you saw the plots for the angular resolution, there was like an increase for high energies. Is this because you only have one telescope and you still need the small array to be deployed, or this is expected to happen again?
Well, I think, if I recall correctly, this is less marked with the stereo, okay? In this case, I think it's simply because at very high energies, you have very large showers. Sometimes they get clipped on the edge of the camera, okay? So it probably can be done better with a more sophisticated analysis, but in the end, what you can gain is really small, right? So this is, as I said, the baseline analysis, and the main reason is probably clipping of the image at the edge of the field of view. Yeah. Not saturation. Saturation is not significant of charge, but clipping. Yeah.
Okay, thank you.
Any other urgent questions? Yes, no? Okay, no. I think we can take one more.
So when you compare MAGIC with LST1, the limitation on LST1 is statistics, or what is the...
No, it's the fact that it's a single telescope. So it's like normal, I mean, as soon as you have a second telescope, you have a stereoscopic view, which means you can, let's say, find what is the distance to the shower, okay, impact parameter, everything. And then there is a huge performance boost with that, factor 2-3 in sensitivity easily, just with a second telescope.
Okay.
With just one, there is a lot of degeneracy between a very bright distant shower and a dimmer, closer one, so this is hard to beat, yeah.
So let me ask the last question. As soon as you have a second one, you will be better than MAGIC?
Yes, factor 2-3 improvement relative to this. MAGIC, I mean, it has also a higher threshold, okay, so for MAGIC this would go up like this. So clearly with a second telescope, it would already be the most performing instrument in these energies, yeah? So end of 2025, 4. Yes. Okay, thank you very much. I think we have to continue. Thank you very much for the talk. Let's thank him. And good luck for the future. Yeah, thanks.
Okay, this is on. Okay. Can you find it? It was downloaded.
Sí, estaba
¿Me avisas cuando tengas 5 minutos?
The next talk will be presented by César Domingo from IFIC, and he will present gamma ray imaging for nuclear astrophysics studies and applications.
Okay, thank you very much. Can you hear me? I think so. Okay. Well, first of all, I would like to thank the organizers for the kind of opportunity to present here our work. I will continue talking about astrophysics and gamma rays. However, in my presentation, I will try to present some experiments, some measurements that we can do in the laboratory with neutron beams, also to understand what's going on in the stars. Now, to motivate my presentation, I have picked up this picture here. Maybe you recognize the Milky Way galaxy, but this is actually a painting. It is the top half of a painting by Anselm Kiefer from Guggenheim. And it's interesting to see that the author is fascinated by the night sky, by the stars, and in particular about its interpretation regarding our origins and fate. And that's interesting because that's pretty much also the same vision that we share in nuclear astrophysics, where we also try to understand the origin and fate of stars and also of ourselves as living beings. Okay, to start with my presentation, I would like to pay a small tribute to two very important discoveries that happened just 90 years ago, 1932. Any guess in the audience? Okay, the first one I wanted to discuss is this one here. So the first nuclear reaction induced with an accelerator by Cockcroft and Walton. Here in the back part, you can see Cockcroft. Walton was sitting there in the cabin observing the traces from the alpha particle in a mica window. And this is a very interesting story because actually, initially they were aiming for achieving 1 megaelectron volts with their home-built accelerator, and they were having a lot of troubles to do so. The main troubles were related to vacuum leaks in the tube. So they were experimenting a lot, and eventually clay, wax, and some sort of plasticine made the job. And they managed to reach to about 500, 600,000 volts. And that was apparently not sufficient. But then Cockcroft realized, or he found a paper by George Gamow, which was discussing the tunneling, the quantum tunneling effect. And then they realized that probably at lower energies, they will manage to get that reaction. And then they went for it, and in a short period of time, they managed to see the first alpha particles from this disintegration. And this is how they actually won the race against other competitors in the USA, like Lawrence with the cyclotron, who could reproduce also these results a few weeks later, and so on. So that's a very nice story, and actually it also illustrates the importance of collaboration between theory and experiment. Okay, the second discovery that happened just 90 years ago was the discovery of the neutron by James Chadwick. And in this case, it's very interesting to see how limitations in equipment were compensated by Chadwick by means of a very thorough methodological research. It's very worth reading this paper. And the reflection I want to make here is that this was the state of the art in experimental neutron physics and in accelerators just 90 years back. And it's very impressive to see that today we have so many ways of producing neutrons, covering almost 15 orders of magnitude in neutron energy, that we can measure neutron interaction reactions in many different channels with a very high neutron energy resolution over those energy ranges, and that also we can manipulate neutrons in a controlled way, as to use, for example, cold neutrons to make imaging of molecules of interest for biology. We can also use thermal neutrons for producing energy and radio tracers for medical imaging. We can combine reactors with accelerators to produce higher energy neutrons and new energy production concepts. So all this is quite impressive to be available just 90 years after these two discoveries. And what is also surprising is to see that despite of these developments, there are still so many fundamental questions open related to neutrons. The first of one, the half-life of the neutron. So we still don't know, after 40 years of measurements, which is the exact or the precise value for the lifetime of the neutron, as there are still 8 seconds discrepancy between bottle experiments and beam experiments with neutrons. And for sure, the answer to this question will provide new insights into dark matter and some other new physics, probably. Now, if you go to the other range of the neutron scale, we still don't know how materials behave when we expose them to high energy and highly intense neutron fluxes. And the answer to that question will be obtained by constructing the new Smith-Donnes facility in Spain, where we will be radiating materials at very high energies and neutron fluxes, and this is data which is required for the development of the ITER and the fusion energy concept. And then if we go to the intermediate energy range, there is also a fundamental question, which is how the heavy elements are produced in the universe, and in particular, what is the role of neutrons in those nucleosynthesis processes. And that will be actually the main topic of my presentation today. So this will be my outline. So I will start with a short introduction to the nucleosynthesis of the heavy elements in the universe. Then we will see how we can measure these reactions induced by neutrons in the laboratory at CERN NTOF. And then I will introduce some developments that we have made over the last years in order to enhance the detection sensitivity in this type of experiments. And in the second part of my presentation, I will discuss some efforts to transfer these developments to the field of hadron therapy. And I will finish with a summary and outlook. Okay, let me start with the global picture here. So I will just try to summarize in one single slide the two main mechanisms of nucleosynthesis which produce all the elements which are heavier than iron. They are summarized here in the periodic table, and you can see here in this nuclear chart the two main processes sketched graphically. So on one hand, we have a nucleosynthesis process which is called the rapid neutron capture process, and this happens in explosive stellar environments where you suddenly have a very strong neutron flux so that you can build very exotic and neutron-rich nuclei. They are sketched here by this arrow here. And then at some point when this explosion finishes, then the neutron flux extinguishes, and then all these heavy elements decay back to the valley of beta stability. Now this nucleosynthesis process has been related to the collision of neutron stars or neutron star mergers, because recently strontium was observed in a transient of one of such events. But there are still many open questions related to the rapid neutron capture process, as if this is the only process contributing to heavy elements, or if supernova also contribute to the heavy elements, and also which are the physical conditions in those environments. So there are many open questions, and part of the answer to those questions will come from future experiments at the FAIR facility or at High Solid next years, where we are trying to recreate in the laboratory those neutron-rich nuclei and measure the relevant nuclear physics properties for those nucleosynthesis studies. Now, on the other side, and in a very different situation, we have the so-called slow neutron capture process, which actually has been identified since many years, since Paul Merrill observed technetium in the atmosphere of red giant stars. This happens in red giant stars, so along some specific evolutionary stages. And in this case, the neutron flux is low, so that this nucleosynthesis process is nothing else than a progressive transmutation of light elements into heavier ones by means of a sequence of neutron capture and beta decay reactions. And this is how stars progressively transmute or produce the heavier elements starting from lighter ones. So my message here is that actually nowadays we have quite detailed models for those stars, and what we do is to perform the nuclear physics experiments, actually neutron capture experiments, and we use this as some sort of reverse engineering in order to constrain the physical conditions inside those stellar models. And you will see what I mean in a couple of slides in one example that I will show you. Now, one of the main topics that is related to this slow neutron capture process is the effect of rotation in massive stars. And actually, it turns out that when you include rotation in massive stars, the classical picture that we have of massive stars, which have this sort of onion-like structure that we see in the textbooks, it changes completely. They find then circulation currents in opposite directions, differential rotation of the core, and in summary, a wealth of mixing phenomena which affect the nucleosynthesis of the heavy elements by orders of magnitude. So eventually, if at some point we manage to make the precise observations of elemental abundances in those stars, and also to measure accurately enough the corresponding neutron capture cross-sections, we will be able also to constrain experimentally those very exotic hypotheses or predictions. Okay, now let me show you how we perform these experiments in the laboratory. So today we'll introduce the CERN ENTOF facility. This is based on an idea by Carlo Rubbia, and actually what we do here is to use the pulse proton beam from the proton synchrotron, and these proton bunches impinge onto a lead block, which is placed here. And at that place, by means of spallation reactions, we get about 10 to the 15 neutrons at that place for every incident proton bunch. Now, what we do for these experiments is to take the neutrons, which fly along a certain flight path of almost 200 meters length. And at the end of that flight path, we set up the sample whose cross-section we want to measure, and we surround the sample by detectors, and I will show you in a few slides how these detectors work. Now, we also have a second experimental station. In both of them, we can cover a full energy range of interest for astrophysics, so from the thermal neutron energy range up to several GeV of neutron energy. And then more recently, we also have built a new station where we can reproduce the stellar neutron spectra, as it is shown here, the Maxwell-Boltzmann spectra, and there we can make measurements by means of the activation technique. But this will be in operation first next year, and I will not discuss it in my presentation. Okay. Also, let me emphasize that here we can have, in this experimental station at 200 meters, we have a very high neutron energy resolution thanks to this long flight path, and still quite a high neutron flux, as you can see here in this picture. In the other station, we have also a high resolution, not as good as here, but a much higher neutron flux. Okay, this slide here is just to give you a flavor on all the measurements we have made at ENTOF since it started to operate in the year 2001. In the different colors, you see different reaction channels that we measured. So in blue, you can see radiative neutron capture channel. These are most of the measurements that we do. In red, you see fission reactions, mostly for new reactor concepts. And in orange, you can see some reactions based on light charged particle emission induced by neutrons, mainly for medical physics and for Big Bang nucleosynthesis. Now, about 50% of the measurements that we have made are related to astrophysics. And I would like to show you and discuss briefly one example of these astrophysics experiments that we did some years ago. This is the neutron capture cross-section on zirconium-93. The measurement at ENTOF is shown here in this diagram. You can see here the capture resonances as a function of the neutron energy. And in colors, you can see the different background contributions, which are actually quite interesting. I will discuss them in a minute. Now, this is an interesting case because zirconium-93 is a radioactive nucleus, has a half-life of 1.5 million years, which is produced in red giant stars. And now the interesting point here is that it behaves as a valve in the flow of S-process matter. And the opening of that valve is regulated on one hand by the half-life of zirconium-93, so the beta decay rate to niobium-93, and on the other hand, by the neutron capture cross-section on zirconium-93, which leads to zirconium-94. So the point is that if we can measure in the lab this neutron capture cross-section, then we can also estimate from the measured cross-sections which would be the abundance ratio of niobium to zirconium. And this has been measured using the Hermes spectrograph in this type of stars. And actually, the result of this measurement is shown here in this diagram. This is this ratio here above 16. And here you can see the error band from the observed abundance ratio. Now, as I was mentioning before, one can compare that observed ratio of zirconium to niobium with the same ratio obtained from the ratios of the cross sections that can be measured in the laboratory. And this is what is shown here with the bold solid line. Now, the overlap of both curves shows the range or the effective thermal range where the S process operates inside these red giant stars. And that's quite interesting because that's a way of combining observations with measurements to extract information from the inside of the star. That is something that you cannot typically access with other type of observations or whatever. Now, interestingly, as you can see here, this thermal energy range that we can obtain from this comparison is actually not constrained from the observation, but it is constrained from the measurement that we did at NTOF. Because as you can see, the main error bar is coming from our CAPTCHA experiment. And this is so because of the high background level in that energy range. So, and actually, as it is pointed out in this publication, if we could reduce or perform more sensitive measurements, then we could constrain the thermal conditions even more. So now the question is, if there is a way experimentally to improve this type of measurements, and this is what I will try to explain now briefly in the next part of my presentation. And to introduce this, I have to show you very briefly a typical true neutron CAPTCHA event looks like this. So you have the neutron impinging on the sample you want to measure. Then you have a flash of gamma rays. So we never detect the neutron because the neutron remains. It is captured in the sample, but you have a flash of high energy gamma rays. And then you have some detectors around to measure those gamma rays. Now the point is that overlapping with that reaction channel, which is the one of interest for us, you have the elastic scattering channel, which actually dominates by orders of magnitude. That means we are doing our measurements in a cloud of neutrons surrounding our setup, and this cloud of neutrons can be easily captured in the surroundings, emitting also gamma rays, which are seen by our detectors. So the point is that our, or let's say, state-of-the-art detectors cannot distinguish between those and those gamma rays. And this is what actually delivers that high background in that energy range of interest for astrophysics. So the idea that we have been developing in the last years is based on replacing those detectors by other detectors that have imaging capability. So detectors where you can see or get information on the incoming radiation direction. And by doing so, you can disentangle between true CAPTCHA gamma rays from the sample and contaminant gamma rays from the surroundings. And a way to implement this is to apply the Compton detection technique, where you basically change or replace your detectors by others which are sensitive to positions and to energies. And then by Compton kinematics, you can reconstruct the origin of the gamma rays and play this game here, rejecting background events. Okay, this is how it looks like when we eventually implemented this idea thanks to an ERC grant. I will not describe all the details because there are quite a lot of technical developments behind this. But just let me emphasize that you can see that now we have moved from a setup with only 2 detectors to a much more complex setup. We have actually 20 detectors, all of them sensitive to the energy and to the position. And these 20 detectors are arranged in 4 Compton modules, covering a large solid angle around the sample that we are using for these experiments. And that is so because you have to enhance detection efficiency as much as possible for this type of experiments. Okay, this slide just summarizes some of the developments we had to make to implement this idea. Just let me perhaps highlight the need of implementing machine learning techniques to reconstruct the 3D coordinates of the gamma ray hits in the crystals, and also the large amount of lanthanum chloride crystals that we had to use, and also the fact that we had to make or take special care of optimizing our detection apparatus for lowest possible sensitivity to neutrons. This is why we were implementing here some polyethylene enriched in lithium-6 that we were testing at CNA in Sevilla and so forth. Everything thought to reduce all possible interactions from that cloud of neutrons that I was mentioning before. Okay, and after all these developments, which I will not discuss in more detail, then, of course, the first thing was to test that we actually can do this imaging. Okay, fine. And this is how we did here. So we have a vertical big gantry where we can place a radioactive source here in front of one of these modules. And now by moving this radioactive source in front of one of those modules, we could reconstruct the position of the source. And then we were quite happy because then we could implement this idea for NTOF. And now actually at that place, we were playing a little bit, also with the help of some summer students who came to IFIC, and then we were moving the radioactive source in small steps in front of our system, and we could then also write letters with that source and also read out those letters with our Compton imager in front of the radioactive source. Now, so this makes us confident that we will be able to remove background sources which have these shapes of the letters, at least. Okay, so for us, it gave us confidence that we could implement this idea for neutron capture experiments at NTOF, and very quickly, the first measurement we did was neutron capture on selenium-79. This is, again, a case of high interest for astrophysics because it is also a branching point which is sensitive to the thermal conditions in the stellar environment. And actually, what I have told you is only half of the story because there is an additional complexity in this type of experiments, and it is that when you want to make a measurement on an isotope which is unstable, then the first problem that you face is that you don't have a sample of that isotope. It doesn't exist in nature, so you have to produce it. And the way we produce it is by mimicking stars. So we actually start from a sample of selenium-78. We put this sample inside a reactor by means of neutron captures. You produce a small quantity of selenium-79, but at the end of the day, you are left with a sample like this, which has a lot of contaminants. It has 3 grams of lead, 1 gram of selenium-78, only 3 milligrams of selenium-79, which is the one you want to measure this reaction rate, and a lot of radioactivity from cobalt-60 and selenium-75. And you have to live with that. So you cannot separate all those contaminants. You have to place that sample in the beam, and that gives you an idea of the level of sensitivity that you have to reach with this type of detectors and with the time-of-flight technique to observe the first resonances on selenium-79. So this is a very preliminary result showing here the first ever measured resonances in selenium-79. And with this data is fully analyzed, then we hope to constrain the thermal conditions during core helium burning and shell carbon burning in massive stars, which are the last 2 evolutionary stages before these stars explode as a supernova. Okay, and at this stage, very quickly, in the last 2 minutes, I want to address the question whether all these developments may have some societal benefit, some social benefit. And actually, for this, I will introduce very briefly the technique of hadron therapy, which, as you know, is based on using high energetic proton or ion beams and exploit the maximum dose deposition at the end of their trajectory, which is, as it is shown here in this picture, can be determined very accurately for materials of non-composition like water. Now, the problem is that when you go to human tissue, as it happens with the hadron therapy facilities that are being increasingly used worldwide, the problem is that you have uncertainties of about 1–3%, and that means that you cannot determine that endpoint with a high accuracy, and therefore in this type of treatments, what you do is that you typically irradiate about 3.5% more of the expected ion range plus 3 millimeters. So you are actually irradiating healthy tissue of the patient. And of course, this can have secondary effects, and this is also especially delicate if you have a sensible organ near the tumor. Now, this clearly shows the need of improving ion range determination in this kind of treatments. There are many groups working on this worldwide. I want to very briefly show the 2 main techniques that are used for this. One is based on using positron emission tomography, because in this type of treatments, you produce positron emitters, which at some point will decay, and the positrons will annihilate, emitting 2 511 kV gamma rays that can be detected with detectors in front-to-front configurations, as it is shown here. Now, this has the drawback that it is an indirect technique. It is a bit delayed because of the half-life of the positron emitter. But recently, using short-lived beta plus emitters, the KBA group has demonstrated accuracies, or let's say range shift sensitivities of about 1.3 millimeters, which is quite promising. Now, alternatively, you have also the possibility to image the prompt gamma rays, which are emitted in those nuclear reactions from the patient tissue. These are high-energy gamma rays. Here, there are also quite promising results. I want to highlight also the results from my colleagues from IFIC at IFIMED. But now, there are also some drawbacks here. For example, when you use Compton telescopes for this technique based on 3 layers, then efficiency is an issue. And also, the intrinsic angular resolution or imaging resolution is not as good as in PET. Now, to make the story short, what I want to say here is that these two techniques are quite complementary, and the question is whether one could combine them both in a single system. So this question was posed, and a possible solution proposed by Katia Parodi 7 years back. This is the system that she proposed, and as you can see, it's quite similar to the one I was also proposing for a completely different application for neutron capture cross-sections of astrophysical interest. But of course, once we had fully developed our system, we were very anxious and eager to see whether this could be applied in this kind of treatments. So I'm running out of time, so I will flash very quickly some proof of principle measurements we did at CNA using a particular phantom made of thin layers of plastic and a thick graphite layer at the end. So from the thin layers, we could, using 2 of our detectors in front-to-front configuration, we could obtain PET images quite accurately, and also from the stop of the ions in the graphite layer, we could also make Compton imaging with the same system, in both cases with a reproducibility of better than 2 millimeters. These results have been just published in this publication here, and also motivated by these good results, we went to HIT, to the Hadron Therapy Center in Heidelberg. In this case, we used 4 of our detectors, and thanks to the higher and the more realistic clinical conditions of higher beam energies and beam intensities, we could also use more realistic phantoms, as you can see here. And again, in this case, we could apply both Compton and PET imaging, and combining them both, we managed to simultaneously make this or demonstrate this hybrid concept of Compton and PET, obtaining a very high accuracy for the PET imaging and a very high statistics, which is important for the real-time online verification of ion range monitoring exploiting the Compton imaging. And this, I'm not coding any accuracy or whatever, because that will be the aim of a publication, which is right now in preparation. And with this, I come to the summary, and since I ran out of time, I will stop here and thank you for your attention.
Thank you very much for this very nice and wide presentation covering too many things. So maybe we have time for a couple of questions, maybe? Yes.
Cesar, maybe I just missed the last point, because you combine both techniques, no, the PET and the Compton.
Right.
What's not clear to me is how do you overcome the problem of the beta lifetime? I mean, the delay in the measurement.
Yeah. So that's a good question. So actually, what we do is to reconstruct the PET image. You have 2 choices. One is to use positron annihilation during the spill. Well, I didn't have to explain, but this is a synchrotron. So typically, you have a spill, that means a beam delivery of a few tenths of milliseconds. In this case, were 30 milliseconds. And then you have something like 200 milliseconds of beam off. So then during the beam on is where you actually can do prompt gamma imaging with the high energy gamma rays. And then PET you can try to do with beam on, but in our experience, this was only possible at low beam energies because otherwise mainly the neutron-induced background is very large. So here you can see in green, this is actually a PET image reconstructed during beam, but at low beam energies of about 50 MeV. Now, when you go higher in beam energy, the background during the spill is so large that in spill it's quite difficult to make positron emission tomography. Then what we do is to use the first 30, 40 milliseconds right after the spill, and that is dominated by the decay of short-lived beta plus emitters, which are nitrogen 12 and some others. And then your signal to ratio is mostly dominated by the decay of that short-lived positron emitter. And then you can still do PET reconstruction actually very accurately. Now, the problem of the long half-life you get when you try to use the full range between spills.
More questions, comments? What is the time scale of these developments?
6 years. 6 years.
How many?
Six years.
So,
a near C grand duration with an extension of 1 year.
Okay. Okay, let's thank Cesar again for this nice talk.
Thank you.
The last speaker of the session is Sven Heinemeyer from IFT.
¿Qué pasa? ¿Está? Sí.
Y si lo ponemos...
Creo que ya... No, perdón. No. Control L.
No, control L.
No. ¿Cómo lo has hecho antes?
Es que como era PDF.
Ah.
No, aquí, pero es lo que hemos hecho antes, sí, ahí.
Aquí.
No, espérate, era aquí, pero eso.
Ah.
Pero es lo mismo.
Sí. Aquí es, no es. How do we go to full screen? La flecha a la derecha.
Muy mal hecho. Sven Heinemeyer, Future Perspective for Higgs Physics and Theoretical Challenges.
Thanks a lot. Thanks a lot for the invitation. Is it? Yeah. I'm very happy to talk about my favorite topic, Higgs physics here. And I will first give you some introduction. I will then talk about what I call the secure future, the high luminosity LHC. the agreed upon future, which will be E plus E minus colliders. I have one short section about theory meets experiment, which also touches upon the other part of the title, which is not reflected here, theoretical challenges, and then finish with some important complementarities. On the 4th of July 2012, the physics world changed, and not only Atlas, but also CMS discovered the Higgs boson. I hope I make CMS happy. We know these plots. By now, we also know that the discovery that was made is a standard model-like discovery. The Higgs particle that was discovered, we have standard model-like, seen here in the various production modes or various decay modes as well. On the other hand, there's a second fact. The standard model cannot be the ultimate theory. And there are several reasons for that. Gravity is not included. There's the hierarchy problem, meaning the stability of the Higgs boson mass with respect to quantum corrections. There's no unification of the three forces. No dark matter candidate is there. The baryon asymmetry of the universe cannot be explained, meaning that why there are more particles than antiparticles. This will play a major role later on. Neutrino mass are not included, and there are some experimental data which are not described well. My favorite one is the enormous magnetic moment of the muon, but this will not play a larger role here. But there are many, many reasons why the standard model can't be the ultimate theory. And putting fact 1 and fact 2 together, there's only one possible conclusion. The discovered Higgs cannot be the standard model Higgs. Of course, this is not the real question we want to ask. The real question is, does the BSM physics that necessarily has to exist has any relevant impact on the Higgs or the Higgs sector? Maybe, are there any interesting hints from LHC results that we can use as guideline or toy examples? I'll do this later. And if so, which model might be preferred? And in order to answer these questions, we have to first, or one possible answer is to check for the changed properties of what I often call the H125, not to call it the standard model Higgs or standard model like Higgs, but the Higgs that was discovered at a mass of 125 GeV. And second part of the answer, to check for additional Higgs bosons. And as we will see, this is important not only above 125 GeV, but also below 125 GeV. Good. So, summarizing the main questions. What are the couplings of this particle to the other elementary particles? Is the coupling proportional to the mass of that particle as required by the Brout-Englert-Higgs mechanism? By the way, I think it's called Higgs boson because Higgs was the only one that predicted that the particle exists. Yeah? Therefore, I think it's justified to call it the Higgs boson. What is the mass, the total width, the spin, and the CP properties of this particle? Is there maybe CP violation involved? What is the value of the Higgs self-coupling? Does it correspond to what we expect from the standard model predictions? Is it a fundamental scalar as in the standard model, or maybe part of a larger structure? Is it part of a model with additional scalar, singlets, doublets, or there's a slash missing here? Maybe it's a composite state. Does the particle couple to new particles with no other particles to the standard model, the so-called Higgs portal models? Is it maybe mixed with new scalars of exotic origin, etc.? Yeah? These are all the questions that we would like to answer. And just to give an overview, what are the options? We can have the standard model with additional Higgs singlets, 2 doublet models with various types. We can have the supersymmetric version of this. We can have the simple SUSY version with more singlets. We can add triplets, etc. And as I was saying, also there are BSM models without extended Higgs sectors, but they still have changed properties of the Higgs, yeah, from the quantum corrections that are involved. For example, standard model plus vector-like fermions, Higgs portal models, Higgs radian mixing, etc. Yeah? So there's a plethora of models that we can investigate, or that we should investigate. Before I get to this, what is the experimental situation? Well, now we have the LHC up and running, so far 13 TeV, now that we are at 13.6 TeV. Maybe we will go up to 14 TeV in the next run. The approved future is the high luminosity, the high luminosity LHC, the final stage of the LHC. I will give you a timeline in a moment. Looking into the possible future, one possibility to extend the analysis is the so-called high-energy LHC, where one should just put new magnets into the existing tunnel. which could get us to something like 27 TeV. The question is this possible in view of the magnet developments? We do not know. Then here underlined are the various E+ E- options. The most developed one is the International Linear Collider, which could possibly be constructed in Japan. It would start with 250 GeV center of mass energy up to 1000. I put in the decision 2020X. First I put 2018, then 19, then 20. I'm tired of this. I just leave the X there. The next possible one is the Compact Linear Collider, which could be constructed at CERN, starting at 380, going up to 3000 GeV. Then coming to the circular machines, FCCEE, which could also be constructed at CERN, which could go up to 365 GeV, where the feasibility study is right underway. The CEPC, the Circular E+ E- Collider, which could be constructed in China, going up to 360 GeV. Maybe it will enter into the next 5-year plan. Nobody knows. And the new kid on the block is something like this C-Cube, the Cool Copper Collider, which could be constructed at Fermilab, going up to 550 GeV. I also saw the number 2 TeV floating around, but I'm not sure about that. And going into the even further future, we could go to the FCCHH, so using the same tunnel as FCCEE, where we could have proton-proton collisions up to 100 TeV. The same possible here is the same as here, because we don't know how the magnet development will go in the future. Good. Coming to the secure future, the high luminosity LHC, this is the timeline. We are right here. Then we have the run 3, a long shutdown, run 4, going to even higher luminosities up to 300 inverse femtobarn. Then the last long shutdown, and this is then the high luminosity run, which here ends at 2038, but with the delays that we had in the past, I'm pretty sure that the high luminosity LHC will keep us busy until 2040. Important point is we can expect about 20 times more integrated luminosity than we have now, and this will allow us to perform precision measurements, look for rare processes, and also make discoveries. Now, what do we expect for the Higgs boson couplings? You will often see the so-called coupling modifiers kappa, and then the underscore is the particle to which the Higgs boson couples. And kappa equal to 1 is the standard model. And the question is, how precise can we get these kappas measured at the LHC? And on the left-hand side, we can see here the various projections from ATLAS and CMS. Not very well visible. There are some gray bars here, which is also here. This is then some additional theory uncertainty. This is better visible on the right-hand side. Red is theory, and blue and green are either statistical or experimental uncertainties. But when one thinks about theory, sometimes we're really theory-dominated in some of them. Yeah, you can see this, and this is part of the theoretical challenges. I mean, here for theory, this assumes already a strong improvement in the calculation. Yeah, it's not what we have now. It was assumed that there will be improvements in the future, and still we can be theory-dominated in these uncertainties sometimes. But one sees also that we get into the several % range for most of these couplings. There are other measurements that will be done. For example, there will be measurements for some CP mixture. I will not go into details. This is a quantity that can be measured, Fa3, that is directly sensitive to a CP mixture of the Higgs boson at 125 GeV. And this can be measured, well, relatively precisely in the range of 10 to the minus 4, but if one looks at theory predictions, one finds that this quantity is actually often smaller than 10 to the minus 5. So we will get some strong improvement, interesting limits, but it will most likely not be sufficient in order to say something about real models that can give you some kind of CP mixture in the Higgs boson that we've seen. The next point is the Higgs self-coupling, the trilinear coupling. And often one sees this kappa lambda, which is the trilinear coupling that is measured, divided by the standard model prediction. And often it's assumed that this value of kappa lambda is 1, meaning that the same value that the standard model predicts of the trilinear Higgs coupling is realized in nature. And if so, one can see in this plot how well this kappa lambda can be measured in ATLAS and CMS and in the combination, which is then this black line. And one gets a measurement, I would put this into quotation marks, at the level of 50%. Yeah, so we get 1 plus minus 0.5 out of the high luminosity LHC. These are the current prospects. It's good, but it's certainly not a high precision measurement. One word about BSM triple Higgs couplings. This has not been studied very much so far, but you can imagine this is the process, glue going to two Higgses, and then we have here these diagrams where the standard model like Higgs or Higgs 125 GeV can contribute. Here's where the triple Higgs coupling comes into the game, and the sum of these are actually used in order to produce this kind of analysis that gives us this black line here. But in BSM models, for example, in 2Higgs doublet models, also other Higgs bosons can contribute, and then BSM triple Higgs couplings can play a role here. And as I said, this has not been analyzed very much so far, but let's look here, for example, on the right-hand side. This is this kappa lambda, and then this is this BSM triple Higgs coupling, small capital H, where this is the standard model point, so 0, 1 is the standard model point. This color coding tells us with which kind of deviation we can expect, how many sigma of deviation we can expect at the high luminosity LHC. And there are parameter regions, depending how you realize the 2Higgs doublet model, where one finds a large deviation. The kappa lambda is standard model-like, but this BSM triple Higgs coupling is not at its 0 value. And so one can get sensitivity to this kind of BSM triple Higgs couplings at the high luminosity LHC as well. Good, so this is what we will have in a couple of years. Well, in maybe 1 to 2 decades, we will all have all these measurements. But what comes afterwards? And I looked here at the recommendation of the European Strategy for Particle Physics update, which clearly states that the next large facility after the high luminosity LHC for particle physics should be in the plus and minus collider. This is where everybody could agree on. Where one could not agree on is which kind of a plus and minus collider. And I've shown you the various possibilities, linear versus circular, etc. This kind of collider is recommended to study the Higgs at 125 GeV, to do top and electric physics, and of course also to do BSM searches. Obviously, this new plus and minus collider will come after the end or maybe in the final phase of the high luminosity LHC. Therefore, the physics potential of a new plus and minus collider must be viewed in the context of the high luminosity LHC results, and therefore they are also often shown in comparison with each other. How can we produce a Higgs boson at any plus and minus machine? This here is the cross section as a function of the center of mass energy. And at lower energies, if you remember this list that I put, all the proposed E plus and minus machines would start at something like 250 GeV. And then 250 GeV, one has this red line. This is the Higgs Strahlung process depicted here on the right-hand side. This is the main production process at the first stage of all these E plus and minus machines. If one goes to higher energies, also the W boson fusion, this diagram here sets in, and then you can see it overtakes here at some point the ZH production. If one does the ZH production, one has this very nice model-independent cross-section measurement. This is something that a plus and minus machine can do, what a PP machine cannot do. When I showed you the precisions for the kappas, always some theory assumptions went in, which to overcome the problem that you can't have a model-independent cross-section measurement. This can be done via this recoil measurement, where one just looks at the Z and doesn't care about what the Higgs does. And from this measurement, one gets the cross-section, and one also gets a measurement of the Higgs boson mass to a very high precision. This is an overview what can be expected for these various kappas that I've shown to you before. We will not go into all the details. The color coding tells you the collider. Gray one is high luminosity LHC. And then, for example, the greenish ones are the ILC. This, burgundy ones or brownish ones is CLIC. Blue is FCCE, and yellow is CEPC. One can see that in most of the kappas, or nearly all the kappas, there is a strong improvement from the high luminosity LHC to E plus and minus. One can also see that E plus and minus roughly gives you the same precision. It does not depend so much on which E plus and minus collider is realized. So often these are very similar. And the best one, of course, is always the dark blue, which is FCCE plus FCCEH plus FCCHH, which is great. We will get these measurements maybe, but unfortunately everybody of us will be dead when these measurements are done. Yeah? So it's nice to have these predictions, but it's really in the very far future. Now, what kind of precision do we want? Yeah, this is what we can get. What do we want? And if one looks at simple models like the MSSM or 2x doublet models, let's say, one can expect the deviation in the couplings to gauge bosons in the sub% range, which is then always also suppressed here with the new Higgs boson mass scale. Couplings to top quarks or charm quarks, a bit higher in the few percent range, but of course also here suppressed and also suppressed with, with another factor 10 beta, which I will not discuss in detail now. And finally, the coupling to bottom quarks and tau leptons, again in the percent range with a somewhat smaller suppression factor. Another example are composite Higgses. Also here, couplings to gauge bosons are expected in the, let's say, percent range. This is the compositeness scale, depending on the size of F. This tells you what you can expect here. A little bit larger, the couplings to fermions here. So overall, couplings to bosons should be measured in the per mil range, couplings to fermions probably in the percent range. If you compare this with the anticipated precisions that I've shown you before, it's obvious that only plus or minus colliders yield the likely required precision. Yeah? So this is a clear reason why we need the plus or minus colliders after the high luminosity LHC. Of course, you not only want to distinguish maybe one BSM model from the standard model, you also want to distinguish BSM models among each other. And this exercise has been done some time ago, 5 years ago already, assuming here the ILC at 250 center of mass energy with 2 inverse Autobahn. And here, well, they picked parameter points in these various models out. Well, standard model, MSSM, 2x doublet models, composite Higgs, little Higgs models, etc. And then these numbers tell you how many sigmas you get from the Higgs precision measurements to distinguish these models or these model points from each other. And green is good, green is above 5, orange is so-so, red is not so good. As you can see here, you go below 2 sigma only. But this must not be the end. If you go to the ILC with 500 GeV and you add this, then nearly everything becomes green. This is the worst one, 3.6 sigma, but effectively you can distinguish all models from each other. And again, this shows the power that the future precision measurements at any plus or minus collider can provide to us. Another example, here it has been analyzed what happens if a BSM point that cannot be directly be tested is realized in nature. It was assumed that the new Higgs boson mass scale is at 1 TeV and 10 beta. Okay, 10 beta is the ratio of the 2 vacuum expectation values that you have from the 2 Higgs doublets in the model here, that this point is realized, and then you do Higgs precision measurements, first at the high luminosity LHC, and the parameter space that is then favored is given by this light pink shaded area, and it doesn't close here, yeah, it extends. This means the precision that you get at the high luminosity LHC will not be sufficient in order to set an upper limit on this new Higgs boson mass scale. This changes once you include E plus and minus measurements. Again, here ILC that at 250 or 500 GeV was assumed. And as soon as you do this, when you fold this in, you get an upper limit, either 2 TeV or 1.5 TeV of the new Higgs boson mass scale, which then sets a clear target for future collider exploration. Yeah? So precision measurements that we hopefully can do in the future will tell us where to look directly for the new states. Next point, the Higgs self-coupling, which can be measured at future colliders as well, of course. Again, here are all the collider options listed, and you can distinguish, well, it's not, something is not very well visible here. There are these light bars and the dark bars. The light bars, they do not for di-Higgs production. Of course, if you have di-Higgs production, obviously a triple Higgs coupling is involved. You can also try to measure the triple Higgs coupling with single Higgs production, where the triple Higgs coupling only enters via quantum corrections. But these are usually restricted to get you to the 50% level or so. Once direct production is possible, and this is by definition only possible at the linear machines because they get to a sufficiently high enough energy, then you can get precisions at the 30, 20, or even 10% level here. Yeah, this can be done. So we can expect 50% from the circular plus minus machines, and depending on the final energy stage, 10% from the linear ones. One caveat here, all this is done only for kappa lambda set equal to 1, which must not necessarily be realized in nature, and I give you one example in the end of the talk where indeed this is not realized with very important consequences. Of course, we not only want to do precision measurements of the Higgs at 125, we also want to look for new Higgs bosons. And I have a few slides on heavy Higgs and a few slides on light Higgs bosons. So first, Higgs is above 125 GeV. This is a benchmark plane in a SUSY model, but applies very similarly to 2x models as well. This is the new Higgs boson mass scale. This is again this parameter tangent beta. This was the area that was covered when this plot was done. But most importantly, the blue and particularly the red line tells us which part of this parameter space can be covered at the high luminosity phase of the LHC. You can see that the range is substantially enlarged here to what is done nowadays. How does it look at the plus and minus colliders? We can have the heavy Higgs production, the new Higgs production, either in association with the Z boson or two heavy Higgs bosons together, normally a CP odd and a CP even one. Yeah, these are the two production modes. If one looks at the coupling structures and at other requirements, one finds that the reach of any plus and minus collider is usually limited by half the center of mass energy, because effectively you can only produce them in pairs, and for some reasons the masses shouldn't be very far from each other, and therefore one is limited by roughly half the center of mass energy. This has been analyzed, of course, also in more detail. This is one example from CLIC, where they looked at the 3 TeV option, and they found that up to 1.4 TeV, which is nearly half the center of mass energy, they can indeed find these heavy Higgs bosons. Yeah? So roughly half the center of mass energy can be reached. If one folds this in, well, one sees that, well, first of all, circular machines won't see anything new above above 125 GeV. Even the ILC at its final stage will cover only a small region. There one really needs high center of mass energy in order to cover new territory here. But if this energy is realized, there are some unique physics opportunities here. Good. I'll skip this for sake of time and come to Higgs bosons below 125 GeV, where many people might think, but this is all excluded. I will show you it's not excluded. And first of all, can we see these kind of Higgs bosons? This here is again this kind of recourse spectrum that I've shown to you before. This is the standard model Higgs, which is now treated as standard model background. And then depending on the mass of the new particle, you can always see this nice recoil peak, meaning we can probably see this kind of new Higgs bosons. This is possible. I take here my favorite hint from current measurements as a toy example to show you what are the physics opportunities at any plus or minus machine. For sake of time, I will not go into details. This is the search for a light Higgs boson in photon-photon, where there is an excess at the 3 sigma level at 95 GeV. And nicely, there's a similar excess in the old lab searches in the BB bar final state at the level of 2 sigma, which is indicated here. And the question is, if such a new Higgs boson exists, what kind of measurements can we perform? And in order to answer this question, we went to a certain model to see what this model predicts us and which kind of precision measurements can be performed. We looked at a model where we not only have 2 Higgs doublets, but also an additional Higgs singlet. Again, I will skip the details. This plane, for example, shows the measurement of CMS here, 0.6 plus minus 0.2, and the measurement at lab, 0.12 plus minus 0.06. This is the 1 sigma ellipse. These are the model points, and you can see that this 1 sigma ellipse is nicely populated. We can do it. This model can fit these axes. This is nice. But what does it tell us about future machines? First of all, this is the mass of a new Higgs boson, and this here is the coupling of the new Higgs boson to Z bosons, and the Higgs is assumed to K to BB bar. This is the old lab limit, and the model points that can fulfill the axes, they live here. It was analyzed that in an ILC at 250 center of mass energy, everything above the green line can be covered, meaning such a model where such an axis is found can indeed be produced, that such a boson can be produced at any plus or minus machine. Can we further study the model? We can study the model by measurements of the Higgs at 125. So if such a BSM Higgs is realized, the properties of the 125 G Higgs boson are changed. This is the coupling to tau leptons versus the coupling to gauge bosons, standard model, LHC, high luminosity LHC ellipse, and again the ILC ellipse. You can see from the standard model there's a large deviation at the several sigma level once the plus or minus precision is reached. We can go even further. I told you we can produce this new Higgs boson, and this is now the measurement of the couplings of the new Higgs boson to tau leptons and to gauge bosons in two different versions of this model. And these little green circles here, these are the anticipated precisions of the coupling. And this will really tell us what is the underlying model. This will help us to pin down the underlying model, which BSM Higgs sector is realized. Good. Let me tell you a few words on the importance of theory versus experiment. We've seen what the LHC has done, that we've discovered the Higgs boson, etc. All this required that we compare what the experimentalists see with theory predictions at the same level of accuracy. And here, for example, the LHC Higgs cross-section working group that was instated 2 years before the Higgs discovery to provide this kind of predictions was crucial. Yeah, it was, of course, the experimentalists that provided this wealth of data. The comparison that we made with theory predictions, and as I said, there was a crucial contributions from this working group. Now, what can we expect in the future? High luminosity HC and then the plus and minus machines will provide very high accuracy measurements. The measurements are performed using theory predictions, and as I said, the measured observables, they have to be compared with theoretical predictions in the various models. You can put here your favorite model that you like. And the full uncertainty of a quantity, of a measured quantity, is given by the linear sum of experimental and theoretical uncertainties. Meaning, the experimental precision can only fully be exploited with theory uncertainties at the same level of accuracy. Meaning, such a theory effort should be seen as an integral part of any future Higgs physics program or any BSM physics program. Not only experiment. We need the theory as well. Sorry. Coming to the final part, which is very short. I told you we need an explanation why there's more matter than antimatter. One possibility to generate this so-called electric baryogenesis, which is, I will not go into details how this works, which was possible during a first-order electric phase transition in the early universe. I'll show you what this means on the next slide. This is not possible in the standard model. It requires BSM Higgs sectors, and as we'll also show you, if such a first-order electric phase transition that is required to have baryogenesis, that is required to have more matter than antimatter, this can then induce gravitational waves, which will be detectable at future gravitational wave observatories, which gives us an interesting complementarity between gravitational waves and Higgs physics. Now, the first-order electric phase transition, when happens like this, we start at a higher temperature, and this is the Higgs potential. We go down with the temperature, a second minimum forms, then there's this barrier here, and when the tunneling through appears, this is when the first-order electric phase transition takes place. In the standard model, it looks more like on the right-hand side, where it's the smooth transition here. So we need BSM Higgs sectors. Once this happens, once we have in the early universe, or this can happen in the early universe, as I said, when we tunnel from the vacuum which is at the origin to the vacuum that is not at the origin anymore, then these bubbles form the early universe, and this then again induces gravitational waves. This can happen actually in 2x doublet models. This was analyzed. This is just one example where this is a parameter scan in the 2x doublet model, two masses, and then in this there are several possible histories, thermal histories of the early universe, but in this area E, which is nicely colored, this is the nucleation temperature, the temperature of the universe at which this first-order electric phase transition takes place. There, gravitational waves can be induced, which are possibly detectable. Final slide. This, in turn, requires that this triple Higgs coupling doesn't have the standard model value equal to 1, but a higher one. And usually you can see this here these are points that fulfill all this. These kappa lambda is more in the range of 2, a little bit above 2, not at 1. Then you can ask, what does this imply for the triple Higgs coupling measurements at the high luminosity LHC? We go down, this worsens the precision. We are only at a 70% precision. On the other hand, at the plus minus machine 500 GeV, we get to a 10% precision. So these points here, they show, first of all, gravitational waves detectable at LISA. And at the plus minus machine, we can really pin down the triple Higgs coupling here. So there's a very interesting complementarity from these two sides. Conclusions. Well, of course, we exploit the high luminosity HC, and then let's go for a plus minus as quickly as possible and work out this complementarity. Thanks a lot.
Thank you very much, Sven, for this inspiring talk. So,
hello, thanks for the talk. You have mentioned, but I am not totally sure, because we talk about the high energy frontier and precision frontier. What about the possibility of relatively light non-standard Higgs in these kind of machines?
I mentioned, let me go back here, this kind of measurement. Yeah, you can produce, if the Higgs is in the kinematic reach, you can produce it as in a plus or minus machine. Of course, it may be discovered at the LHC, but no precision measurements can be possible. Only very few channels actually are accessible. At the LHC, for light Higgs bosons, the photon-photon final state and possibly the tau-tau final state can tell you something. But there's not such a precision measurement like for the 125 GeV Higgs boson. This doesn't seem to be possible. At the plus and minus machines, you can do this kind of measurements. This is just one example. We can do really precision measurements of the coupling of this new Higgs boson.
more questions to Sven?
Yeah, thanks, Sven. So you showed us a clear roadmap to get to the experimental precision for the Higgs physics with the new colliders and so on. But you mentioned that the theoretical uncertainties are crucial. So what is the strategy to get there, and what are the main challenges in that respect?
I was doubting whether I should put more slides on this, but this was already tough to squeeze in, and going to theoretical details would require much more time. But effectively, we need higher order corrections. Yeah, for example, we have, when one looks at the kappa measurements nowadays, we have uncertainties at the level of a few percent. Usually one-loop calculations, some two-loop calculations are included. There we have to go higher even to match the high luminosity LHC precisions. Going to plus and minus, we need the production process like this one here. This process is here. They have to be calculated. We have full one-loop. Very recently for the standard model, a full two-loop calculation became available. We possibly need some higher order corrections still there as well. And this does not, well, there's also the complementary process that I was showing to you. This one here. Once we go to higher energies, also this has to be evaluated at higher precision. One loop is available, two loop is not available, but we will probably need this as well. Higgs decays also have to be improved, probably one loop order higher. The problem is that the techniques that are necessary to do this are not there yet. One can estimate that theorists get the right ideas, and it's more a problem of motivation. Yeah, if we now say, okay, this E plus minus machine will be built in country X in the year Y, I'm sure that many theorists would start to do this kind of calculation. Before we don't have the security, the motivation may be lacking to do this really tedious calculations, because people can spend a lot of time on one of this decay or one of these production processes, yeah? And they need a good motivation to do this. So there we need a bit more motivation from our, I don't know, funding agencies or whatever. Yeah.
Yeah, it's more a comment than a question, and maybe a bit pedantic. You did very well, I think, on the discussion of the Higgs that was ordered from you, but we shouldn't forget, of course, that there's more physics that these machines can do than Higgs physics alone, and you could do another talk on the Z-pole and on the top production, etc. And there are other colliders that can do things still this century. The muon collider you haven't discussed, plasma wave field acceleration, maybe. Right, so it was a very good topic, talk on the topic that you were given, but it's
yeah, sorry that I
not the full
didn't
story.
talk about the topic that was not given to me.
Yes,
But
exactly.
Let me make one remark about the muon collider, because recently I gave a similar talk where it was explicitly requested to talk about muon collider as well. And a muon collider combines two nice things. Yeah, it's a clean environment and it can be relatively compact. Yeah. However, from the technological point of view, for me, this always comes after E plus and minus. Yeah, I don't see that it can compete from the time scale or so with an E plus and minus machine. It's really so much more advanced. It would be great to have one. I would love to have an E plus and minus collider, but I see it really in the very far future.
Right, yeah, I think you're right. For the Higgs studies, the Higgs factory that we're supposed to build first, I don't think it's a serious contender. Yeah. It is an exploration machine that maybe competes with FCCHH.
Maybe.
Any final comment or question to Sven? If not, I think we can thank again Sven. And all the speakers of the morning, of this plenary session. And
one thing, now that we have the lunch, you can leave your stuff here. This room will be locked. The lunch is in Osteria Cookie or Cardinal School, so we need to cross the street and climb the stairs. If it is raining, there is a path that minimizes the uncovered route, so follow us.
Sí, ya lo sé, conozco.